All right, in this video, I'll be explaining a very nice problem from the Baltic Olympiad, um, problem A called graph. And no, I did not get this problem by myself. Do not think I am good by any means, but this problem was so nice. Like it's a 2100 code forces problem, but the solution is not even that hard to understand. But just the way that you turn what is a seemingly very difficult problem, the way that you turn it into a very easy, common coding problem that's essentially universal or like well known is just mind blowing. So I decided to show it. But essentially, read the problem, just pause the video and understand it. It's really a basic problem, but quick recap is essentially each red edge means that the sum of all nodes connected to that edge has to be one, each red edge, and then for each black edge it has to be, for each red edge it has to be two, and then for each black edge it has to be one. The idea is that you want to minimize the sum, the absolute. So basically, for each node, you'll take the absolute value of that node, and then you'll sum everything up, and you want to minimize that quantity. So let's just say that, for example, the value of you basically want to minimize this, right? So this is absolute value plus value at two. And then I'm very lazy. I know dot 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 plus value at four. Um, the absolute value at four. You want to minimize that quantity basically. So at first I thought, well, this is a very trivial problem. Why is this a 2100 code forces problem? Because this is basically what my thought was, and it is a valid thought. It just doesn't work in all cases. I was like, suppose that in the suppose that in the optimal solution, my bad, comma, oops, bruh, comma, the value for node 1 is x, right? This isn't invalid because we're just saying it's a variable. We don't know what it is, but we're going to say suppose that it's x. Then if we can find another linear form of x, well, we can easily find x by solving an equation. Because the idea is that, okay, if this is, and let me show you how this plays out, right? So the idea is that, like, if one is x, right, then we know that 3 has to be 2 minus x, right? Because we know that the sum has to be 2. So yeah. And then after this, we know that the sum has to be 2 here. So then this has to be x because the sum has to be 2. And then we know that we have another linear form of x because we know that if this is 2, then 1 also has to be 1 minus x so that the sum of these two nodes are also 1. But then we've now gained two different linear forms of x, and we know that, like, obviously node 1 has to be equal to node 1, right? By the reflexive property of equality. Therefore, we can say 1 minus x is equal to x, thus x is equal to 1 half. Therefore, x is 1 half. So then you're like, what's the point of even minimizing it? Isn't there just one solution? But no, this is only in the case that you can set up an equation. Like it's important to note that you might not be able to set up any equation like this all the time. And you're like, because the idea is that, like, this logic only works in cycles. Actually, I might be wrong. It might work in different stuff, but you notice that it's obviously going to work in like a cycle because, like, if one is, like, for example, if I have like a node here, and, like, let's say this is a node, right? And if it's connected to two different things, right? Like, not even that. If it's as long as it's connected to two different things, you can easily, like if it's connected like in a cycle, you can easily get two different forms for that node. So it's very obvious to see that it works in cycles. But a very, like, an edge case that basically destroys this entire logic is, imagine you just have like let's say you have this node connects to this node, right? And then there's a node here, there's a node here, and then you have this as well. Let's say you have let's say you just have a line, right? So each one of your connected components is just a line. Well, then obviously this logic is completely destroyed. So like basically this is not going to work, and it doesn't really take that much thought to know that this is not going to work for everything. I thought it would, but then I realized, wait, no, this doesn't actually work for everything. So basically the idea that you can, and also I should mention that we are going to solve this problem by solving it for each of the connected components. Because like obviously like if I have, like, let's say in this graph I had more edges, right? And then this is another connected component, 5, 6, 7. Obviously this connected component is independent of this connected component. Therefore you're just going to solve it for each connected component. So you'll just like DFS each to find to go through each connected component. You just use like DFS. So like yeah, like through DFS, right? I think that's kind of obvious. But yeah, so this logic doesn't work. So how do we then generalize this so that it works for any such case? Well, then notice that let's say we have a connected component. I claim that we have a connected component. Let's call this connected component um let's call this connected point C, okay? And in C, we have all these nodes, right? So we have for I claim that for connected component C, for a connected component C, just say let me just not I'll just say it. So this means connected component, right? Let's say we have a bunch of nodes, right? Let's say we have n nodes, okay, in this connected component. I don't know. Let's just say we have n nodes. Well, then each one of these nodes, or technically n's already used here. So I'll just use j. Let's say we have j nodes, okay? Let's say we have j nodes, right, in the connected component. Each node can essentially be expressed by a linear term, right? A linear term. Like, and that's kind of obvious because the thing is, we can still use the method of attack to fix a node to be x, right? So if I fix a node to be, so basically the idea is that let's say it has j nodes, so j nodes. So we realize that if I fix a node to be x in C, then each one of the nodes are now expressed are now expressed to linearly. Or each one of the nodes of the nodes can now be expressed linearly. Like the idea is that they can be expressed in the form of mx plus b. So I can basically have so basically what I'm going to have is m1 x plus b1 m2 x plus b2 all the way to the jth node in this connected component, because we claimed that they were j nodes to begin with. So all the way to mj x plus bj. Then the next crucial observation is to realize that m1 is only is so the next crucial observation is to realize the next observation is to realize that m is in the set, or let me see, and n is -1 or 1. Like the reason for this is because like it's very obvious, right? If I fix a node to be x, if I just fix one node in the connected components, it literally does not matter which node you choose in your code, by the way. But if I just fix one node to be x in the connected component C, in basically in C, then I realize that like But you obtain a linear expression by each node by doing c minus, like for example, if I do x, right, then like if I fix the first node to be x, then I contain the next linear form by doing c minus x, right? And then c is either one, or let me not use c because bruh, that was a bad design, but by doing a constant term minus x, because the constant term is either one or two, right? You obtain the next linear form. And then you obtain the next linear form by doing a constant minus the constant minus x. So the idea is that so essentially the idea is that you're going to be obtaining linear forms by just doing a constant minus something that already has a coefficient of 1 in front of m1. Like for example, the coefficient in the linear term, the coefficient is always 1. So basically it is that you, like, let me write this down. To prove this, we know that we obtain linear expressions by doing a constant term minus a linear term such that let me move this, erase this, oops, let me just put this there, I guess. All right, such that linear term has has a has the linear such that linear when I say linear uh linear expression, such that the linear term in the expression, my bad, has a coefficient of 1, right? You know that it's basically, you have a constant term 1 or 2, then you basically subtract it by basically you basically, what I'm saying is you subtract constant term minus some mx plus b, right? That's basically what you do, because we know that like this has to add up to the constant term, or it has to add up to 1 or 2. Therefore, you're always doing that. And since we started with the coefficient of 1, you notice that the constant term will never affect the linear term, because the constant term has a degree of 0. Thus, it will never affect higher degrees. The only thing that it's going to affect is other constant pieces. Therefore, we just prove that m is either -1 or 1. So instead of doing this, we can now simplify this to being we can now simplify this question. We can now just take away the m1s, because we know that it's either -1 or 1. But then you also realize that should have mentioned this earlier. You also realize that we also only care about the absolute values of each one of these nodes, right? We only care about the absolute value. And the idea is that, since here is the elegant, the absolutely mind blowing, like not even trick, just the mind blowing observation, since we know that its absolute value, what we can do is, like, we know that I can basically like eat, like let's say there's two cases, right? X is -1 or x, right? So let's say I have like x plus so I don't, so basically I don't know. It can either be in the absolute value. It can either be b1 plus x. Like, let's just take this for this node right here. It can be two cases, or it could be the case where it's -1. Notice that what we are going to do is, but let me note that like this, like um, let me note that like what we can do here is that, like, if we're doing b1 minus x, what we do is we write each one of these as like a difference of x, right? Instead of writing it as plus x, we write it as b1 minus x, right? We always write this as, we treat this as b1 minus x, because we know that, like, for example, like let me try to explain this with like actual numbers, right? Like, let's say you have this, right? You have 2 plus 5. You're trying to find the absolute value of 2 plus 5, right? Well, I can also do this is also the same as if I was just doing let's say I made this negative. It's also the same as if I did negative 2 minus 5, right? If I had like negative 2 plus 5. It's also the same if I did 2 minus 5. So the idea is that what we're going to do is that we're always going to write the thing inside the absolute value such that the coefficient in front of x is negative 1. So the thing is basically what I said, for each node, comma, we will always write the I don't even know what it's called, just the quantity or the linear um expression inside the absolute value such that the coefficient of m is always negative 1. And you'll see why we do this. But just hang on, right? So we always write it as this. Because basically we know that we can always do this. We will always be able to do this. Because even if x was positive 1, we just multiply it by negative 1 because we know that like multiplying it by negative 1 we're still going to have the same thing. We know that we can just write it as b1 like minus mx1. So basically let's just say we have so then basically it comes down to just doing this, minimizing b1 minus x plus b2 minus x all the way to b j minus x. And then you're like, what can we do? Well, then we could just basically just treat this as minimizing. We could basically treat this problem. We could treat this problem as we have like we can view this expression as we have a number line, and basically we have x, right? And we have like I don't know b1 here. Let's say we have a bunch of stuff. We have b1, let's say b1 is located, this is arbitrary, we have b1 here and b2 here, b3 here, bj here, whatever, right? We have a bunch of stuff. Then we basically treat this problem as just minimizing the sum of the distances to x, right? We basically minimize the sum of the distances to x. That's basically the problem. We've now reduced it to that problem because b1 minus x means just take the distance, right? Therefore, we're just trying to minimize this sum. And how do we do that? Well, to do that, we pick x to be the median in the number line. So we pick x to be the median value in the number line such that it splits the data like like there's the same amount of numbers on one side than it is on the left side. So this will minimize this expression. It will minimize the sum. Well, no. But this is a very common problem. So I'm going to prove it, but like notice that if you've done problems, stick links. See, I've already done this problem, but like look, um, the problem. This is the problem. This is we've literally reduced this 2100 code forces problem into this problem. If you remember this problem, this is this absolute same thing. And it's crazy because this problem was so easy. This is like was such an easy problem. And we've just reduced, this problem is just this problem. But this problem is in disguise. So that's what I'm saying. It's so crazy how we reduced such a difficult problem into an easy problem like stick links. I recommend you do this problem because you'll see exactly what I'm talking about. So we just pick x to be the median value in the number line. Therefore, it's always minimized. Um, let's prove this though, because like I want to prove this because I know there's gonna people like, why is this true? Well, let's do cases. So if I told myself like, if you move x, you can either you if you said, oh well, let's do proof by contradiction. Let's claim that there's two cases to prove this through contradiction. Let's claim that it's optimal, like x is in the median, right? Let's claim that it's optimal to move x to the left. So x is here. If x is to the left, let's say it's optimal to move x to the left by k, right? By k. So then this place is x minus k. That means that all these distances here, like so, um, and you notice that since x is the median, um, uh, since x is the median, then let's say there's let's say there's x is the median value in the number line. Let's say that there's let's say that there's k values here, or not k values. Let's say that there's I values here, and there's I like b1s and b2s, or and then there's j values. So there's I values to the let me use L and R actually. So let's just there's L values to the left and there's R values to the right. Let me note that for everyone, for all the r's on the right, all the distances increased by r times k, because now you have like a new k, and then all the distances decreased by um l times k. And then yeah, because and then it's just gonna be r um times k minus l. And then you prove, and then you know that this is basically the gain of distances. And then you note that k minus l is positive. K minus l is positive. And therefore, if k minus l is positive, you've gained more, right? And you can apply the same logic. If it was x plus k, then you know that it's going to be lk and then minus um lk minus rk. So then it would be actually, did I do this wrong? Oops. K r minus l. Actually, you prove that r minus l here. And then if you do the right case, it would be x plus k. And then it would be these distances would gain l plus k, so it would be l will be k l minus r. And then this would be your so actually then I think well then I might have actually messed this up. Well, okay. Well, then one of these have to be positive. Then the idea that like L has to be greater than R. Then I'm getting R has to be greater than L. Why am I getting two different things for these cases? Okay, so I kind of messed that up. I don't want to ruin the. I don't want to re-record. I think I messed up the proof of why we pick X to be the median value. But whatever. I'll do a separate video on that actually. I have to. I'm not gonna like yeah, I'm not gonna just do this entire video just because I messed up one part of this one section of the video. In I'll do like a different. I'll do another video proving why this is the case. I think I just did something wrong because I got like literally two different things. And but it doesn't really matter. I knew this was true because I did this type of problem, and now now I probably look like a fool because I said this problem is very easy. But like I already had that type of intuition. I guess this problem is easy, but like it's not necessarily easy obvious to prove, but it's still an obvious problem. You probably would still get the problem. But I basically wanted to show you that like um, a 2100 code forces problem can literally just be simplified to a problem set called stick links. And this problem is a very easy problem. Like I know I messed it up, but just because I don't want to restart this, I'll just do another video on why this is true. Because I already messed up the proof, but yeah. Anyways, that's it, and thanks for watching. It's a very messy video at the end, but whatever.